All right, this is the video for 4.1, 4.2. Just some different problems I found in WebAssign that were similar but not exactly the same as your homework. Starting with this number one, and this section is where some of the calculus really starts gearing up and we start to see how calculus can help us see how statistics works. So the actual tracking weight of a stereo cartridge that is set to track at 3 grams on a particular changer can be regarded as a continuous random variable x with the following PDF, so probability density function. It is f of x equals, and then on the top line we have k times the quantity 1 minus, and then quantity x minus 3 squared, close both of those parentheses. That's true from 2 to 4 for x, and then 0 otherwise, so 0 everywhere else. So remember, this is how the probability breaks down on that interval from 2 to 4. And that is continuous because we're on a real number line, so all values between 2 and 4 are possible. It says to sketch the graph of this f of x. Well, to be able to sketch this, the first thing you really, I feel like you need to do is to, especially to get an idea of the height, because all of these go from 2 to 4 on the choices. I would actually do this first part down here, find the value of k. And for this to be a probability density function, there to be a legitimate one, the integral on a continuous function from our start to end for our area, that has to equal 1. So if we can prove that, then we'll be able to show that we have a legitimate PDF also, and we'll be able to solve for that value of k. So the true part is that from negative infinity to infinity of f of x dx should equal 1. So we're going to set our integral, which ours is only defined from 2 to 4, of our function, which is k, parentheses, 1 minus quantity x minus 3 squared dx equal to 1. Now k is a constant in this scenario. It's not our variable x. It's a value we're trying to solve for. So we can pull constants, remember, out to the front when we're integrating. So k from the end in the integral from 2 to 4. And I would actually FOIL this out. This is x squared minus 3x minus 3x is minus 6x plus 9. And then distribute that negative. So we have minus x squared plus 6x minus 9 dx equals 1. We can combine that 1 and negative 9, just cleaning this up a little bit. That's negative x squared plus 6x minus 8 dx equal to 1. You can divide by k, get that over to the other side. And then we're going to integrate this. So we're going to take an antiderivative and we're going to evaluate it. Remember, at the endpoints of, it'll be capital F of 4 minus capital F of 2, where that's our antiderivative, remember. That's using the fundamental theorem of calculus. So we have, that's going to be negative x to the third divided by 3 using the general power rule for the antiderivative. For this one, you'll raise it up to, you add a power and then you divide by that number. So that will be 3x squared, because we're going to be dividing by 2. And then minus 8x. We're going to evaluate that from 2 to 4 so that we can solve for k. So if we plug in for 4, we're going to get f of 4. Let's write this down first. F of 2 equals 1 over k. So 4 would be negative 64 after we cube it over 3, plus that's going to be 16 times 3, so that's going to be 48. Negative 8 times 4 is negative 32, minus my second one is going to be negative 8/3, plus that's going to be 4 times 3 is 12, minus 16, close my parentheses, all equal to 1 over k. Now I'm running out of room, so I'm going to write this up here. If I combine like terms and distribute my negative here, I'm gonna get negative 64 thirds plus 8 thirds is actually negative 56 thirds. And then we're gonna have 48 minus 32 is 16. And negative 12 plus 16 is going to be plus 4. Just continuing to work this out. That's going to be negative 56 over 3 plus 20 over 1 equals 1 over k. We can get a common denominator, that's negative 56 thirds plus 60 over 3, 1 over k. So I'm getting 4 thirds equals 1 over k, which means k equals 3/4 if you flip that reciprocal. So my k value is 3/4. Now, why is that helpful for the graph? Well, let's go back up and look. So if we look at our graph up here, our options, we know that if you know from algebra class, so going back a little bit further, we can look at this and say, okay, this is now 3/4 or 0.75 bracket 1 minus parentheses x minus 3 squared. And this is going to have, if we distribute this, this is 0.75 minus 0.75 x minus 3 squared. I like to write it a little bit differently. So this is a negative 0.75 x minus 3 squared plus 0.75. What's nice about seeing it in this format, I will leave it like this when we evaluate things though, is you can see the negative, and this is just transformations of functions, parent functions. So that negative in front of this part that's squared, that tells me I'm going to be reflecting over the x-axis, which is why all these graphs are kind of parabolas upside down. We know that we're shifting right 3 because of that plus 3 inside. We know that we have a vertical shift up 0.75. Now, and I think that's the only thing we needed, this vertical shift. Because if you look at the different heights here, we have that this height is at, because this right here should be my vertex. The inside of this is the opposite sign and then exactly the vertical shift. So 3.75 should be my point. So it's not going to be this one because that only goes up to 0.4. 3, that might be close. That looks like it could possibly be 0.75. Let's check some of the other ones to make sure they're not. Yeah, this is over 0.8. And this one's just right at 0.6. So it's going to be the second one on the top. That's got the correct vertex. Okay, and now let's talk about some probabilities. So it says, what is the probability that the actual tracking weight is greater than the prescribed weight? Well, the prescribed weight was 3 grams. So what is the probability that x is greater than or equal to, or actually we can just do greater than. When you're on a continuous function, endpoints don't matter. So those two actual questions are the same thing. But the probability that x is greater than 3, well, that's right here at your symmetrical point. That's your vertex of your parabola. So you don't really need any special formulas for this one, because if this is a symmetric graph, which it is, it's a nice even parabola, that means 50% is going to be on each side. So you could do it with an integral, you could, but you don't need to for this specific one because it's obvious that it is going to be 0.5. If you wanted to prove that using integration, you would need to do from 3 to 4, because that's where the integral goes from, and then you would plug in our new k, which is 3/4 or 0.75, whichever way you want to write it since it's terminating. And you would need to do the integration and evaluate that, but we already know what this integrates to because of our previous problem. We just know it's got a 0.75 now in front of it. So we already have the formula for that. We would just need to plug in f of 4 minus f of 3. Now, for this one, this is worded a little differently, and we are going to have to do some calculations. So it says, what is the probability that the actual weight is within 0.25 grams of the prescribed? So that can go in either direction. That could be 3 minus 0.25, or it could be 3 plus 0.25. So our probability question that we're asking is if we are going from 2.75 to 3.25. Okay, and so I am going to do my integration on this one, except we've already done most of that work. I'm going to write what it looks like, and then I'm going to go straight into calculating it. Because the only thing, like I said, that's changed is the K, and that was out front when we did our integration earlier. Okay, so we knew from previous, it's going to be 0.75. And then we're going to have to do, because I'm looking at this as our reference, right? We had our K was over here, but really the K would have multiplied times both of those. So it's 0.75 times our F of 3.25 minus our F of 2.75, where those are our antiderivatives that we found. And remember, our antiderivative was negative x squared, or cubed, sorry, divided by 3. And then we had, I'm looking over here, plus 3x squared. So 3.25 squared. And then minus 8 times 3.25. That's going to be my first one. And I still have this 0.75 out front. Minus, and then I'm going to have a second parentheses, and we're going to have negative 2.75 to the third divided by 3. Plus 3 times 2.75 squared minus 8 times 2.75. Now, a lot of this is just going to be calculating this on your calculator. So working out all of the inside parts, before I multiplied by 0.75, I ended up getting, this was I want to say 29775. Let me double check my last step right there again. I don't think that's correct anymore. No, it was 0.489. Sorry. I had another version of this earlier and it changed the numbers on me when I went to make the copy for everybody. So it's 0.4895 833.7 times the 0.75 out front. All right, I never have enough room with WebAssign stuff to write. So this ended up being 75% of this was 0.3672. So to 4 decimal places, that is part D. All right, for part E, it actually says, what is the probability the actual weight differs from the prescribed weight by more than 0.6 grams? Now, the way they've worded that, it makes you think they're saying only more than, but it just says the actual weight can differ from the prescribed weight by more than 0.6 grams. That could be in either direction. So this could be the probability that X is greater than or equal to 3.6, because that would be more than, and you could, like I said, you could just do greater than if you want, because like I said, endpoints do not matter for continuous functions. But you could do greater than 3 by 0.6, that'd be 3.6, or it could be the probability that we went below 3 by 0.6, so that'd be less than 2.4. Now, because this is a symmetrical shift around the mean, which is in a symmetrical parabola, you could just calculate one of those and double it, which is what I did, but that's only true if your graph is symmetric like ours is. If not, you would need to do both integrals and work those out. So I'm going to do the first one, which was the greater than one. So 3.6 to infinity is greater than f of x dx. But we only go from 3.6 to 4, since that's where our domain stops. And we're looking at our function f of x dx, which we know is up here. And we already know what that is, so I'm not rewriting it all in because we have our rules here. So it's 0.75, and we're going to be doing negative x cubed over 3 plus 3x squared minus 8x from 3.6 to 4. And that's going to be 0.75. And then we're going to do f of 4 minus f of 3.6. And that's just plugging these numbers in, just like you would do a regular integration problem when you do that in calculus. So for the first one, I got, just to save time of writing, I got negative 5.333333. It keeps going. And then minus, and for the second one, I got parentheses, it's also going to be negative, so negative 5.472. So that's going to turn into plus plus right here. So we end up getting 0.75 times 0.1386667, which when we multiply that together, that comes out to about 0.104 and then a bunch of zeros. I think it's like 3 or 4, but I'm just going to the third one after that. Now that's only for the probability that X was greater than 3.6, okay? Because this is symmetric, this is going to be double that. So 2 times that area is 0.2080. And like I said, if you hadn't had symmetry, or if you're not even sure if you have symmetry, maybe you're not 100% sure of that, you would have done the integral from negative infinity to 2.4 as well, which would have just been from 2 to 2.4 for us, because our domain started at the value of 2 for our areas that we had under the curve. Okay, so let's look at this second one. This is, I only have 3 in this section because of all the integration that takes a little bit of time. So this one says, in commuting to work, a professor must first get on a bus near her house and then transfer to a second bus. If the waiting time in minutes at each of the stops has a uniform distribution with A equals 0 and B equals 5, then it can be shown that the total waiting time Y has the PDF below. So this is our probability density function. We are going to have f of y equals 1 over 25y if we're in the 0 to 5 minutes, because that's our waiting time. It's going to be 2/5 minus 1 over 25y if we're between 5 minutes and 10 minutes. And then 0 if we're either less than 0 minutes or greater than 10. So that's the otherwise case. Then it wants us to sketch a graph of the PDF of y. Now, since we don't have any missing like K or C constants in this one, you could just directly get the values and see how this plots. So you can do a little table of values if you want, and do the values from 0, 1, 2, 3, 4, 5. That's going to go to this first function. And then you could do a second one. And I did include 5 on this one because it's an endpoint, but it's actually an open circle. But you're going to see that it overlaps with this one, so that's going to end up being a moot point. This is also open technically. Or actually it's closed on this one, sorry. Yeah, you have to check to see if you have the equal to or not. So if you're doing 0 to 5, and again, I know that 5 is not included in this region, but we do want to know where it stops at, and that would be an open circle if we were doing graphing in like college algebra. But if we plug these in, this is going to be 0, 1/25, 2/25, 3/25, 4/25, and 5/25 is 1/5. Now, if you look over at the second part, this is going to be, if I plug in 5 here, that's going to be 1/5. That's 2/5 minus 1/5. So that's also 1/5. So these are going to match up. So our ending and our starting of the next one match. So we won't see that open circle because this one is closed. We'll have 2/5 minus 6 over 25. So we need to get a common denominator there by multiplying this by 5 over 5. So that's 10 over 25 minus 6 over 25. That is 4/25. And then you'll notice a pattern. When we get to 7, it's going to be 10 over 25 minus 7 over 25. So you get 3/25. Essentially, it goes back down the line, and you can check those. 10 ends up being 0. So the graph that matches this is the one that has the V shape for the second one right here. So notice that we start at 0, 0. In the middle, we're at 5, and 1/5 is 0.2 as a decimal. And then we go all the way back down to 0. So that is the correct graphic. Let's look at our next part for this one. we get past all the graphs, verify that this is a legitimate PDF. That's what that's saying there. It says verify that on the entire domain of this probability density function that it will integrate and equal to an area of 1. So since ours has pieces, we're going to break this up into parts. From 0 to 5, we're going to be integrating 1 over 25y dy, plus we're going to also have to add the area up from 5 to 10 of the integral of 2/5 minus 1 over 25y dy. And then remember, when you do the power rules with integration, you're going to be doing add a power, divide by the number. So you add this up and make this 2. And when you divide by 2, that's actually going to make that a 50. It's going to double the bottom. So this first one is y squared over 50 from 0 to 2. We're going to have to do our substitution in there for a second. And then this one will be 2/5 y, because a constant will get the variable, minus, and that's the same as what we had before, but it's a minus this time. So that's y squared over 50. And we'll evaluate that from 5 to 10. So that's what this first line right here is. It's showing that we're doing y squared over 50 from 0 to 5, and 2/5 y minus y squared over 50 from 5 to 10. Going to work those out. Now they already did the first one for you. They said it's a half, but we can show our work. That's going to be f of 2 minus the f of 0 for that first one. And then again, we have to stick to the one we're on. So this will be f of 10 minus f of 5, working within that group. So that is, let's see, 2 over, oh, that's supposed to be a 5, my bad. I knew that didn't look right as soon as I wrote it. It just looked too small. It's 0 to 5, not 0 to 2. I don't know where I got the 2 from. So we're going to be doing f of 5 minus f of 0 for this first one. So this is 25 over 50 minus 0. So that's where that 1/2 came from. And then for the 10, if we plug in 10, we're going to get 4 minus 2 for this first part. We plug in 5, we're going to get 2 minus 1/2. And notice that's 4 minus 2 minus 2. So the 4 minus 2 minus 2, it cancels out to 0. Minus a negative would be a positive 1/2, but we do have that minus sign in front. So that's going to be minus a negative. Oh, wait, I already distributed it when I was talking. Hang on, let me double check myself. Yeah, because we should get 1 and it's a sign change. I just need to make sure I have, oh, that was a plus. Sorry, I do not have my contacts in right now, and obviously that was a bad move. All right, let me rewrite this. I did not carry my plus sign over correctly here in the middle. We have subtraction because of the fundamental theorem of calculus between these, but this was a plus because it's the first integral area plus the second integrals area. So this is 1/2 plus, and then this equals positive 1/2 in there. So it does equal 1. All right. So what is the probability that the total waiting time is at most 3 minutes? So we're looking for probability that X is at most 3. So then you just have to know which one am I going off of? Well, 0 to 5 is where this less than or equal to 3 would completely lie. So we only need to integrate from 0 to 3 of the 1 over 25y dy, which we already know is going to work out to a y squared over 50. And we're going to work out our fundamental theorem of calculus. That's going to be 9 over 50 minus 0 squared is still going to be 0 over 50. So 9 over 50 divided into a decimal would be 0.18 for this first one right there. Now, what is the probability that the total waiting time is at most 6? Well, that's a little different because that's going to spread over 2 of our different domain chunks. So we'll have to do 0 to 5 of 1/25y dy, plus we'll need to do 5 to 6 of the 2/5 minus 1/25y dy. Okay, for the first one, we know that that one looked like y squared over 50 from 0 to 5. And for my second one, I'm going to be plugging in to 2/5 y. That's a plus again. I keep writing minus. And then minus y squared over 50. And that's from 5 to 6. So for the first one, we get 25 over 50 minus 0. And then plus, this one's going to be, let's see, 12/5 minus 36 over 50 minus, because fundamental theorem of calculus, that would be just 2 and 1/2, so minus a half. So I have 1/2 plus 12/5 minus 36 over 50 minus 2 plus 1/2. So we can add the halves together and get a 1, and that'll be a minus 1 then. So 12/5 minus 36 over 50 minus 1. And when I work that out, I get 0.68. Oops. I wrote it on the line, wrong line. Okay, what is the probability the total waiting time is between 3 and 6? Well, we don't need to go to the integration here because we've already got less than or equal to 6 and less than or equal to 3. So probability of between is the probability that we're less than or equal to the larger one minus the probability that we're less than or equal to the smaller one. So this is going to be 0.68 minus 0.18 or 0.5. And then what is the probability that the total waiting time is either less than 2 or more than 9? Let's change colors. So probability that we are less than 2 or the probability that we are more than 9. That's going to be the integral from 0 to 2 of our 1/25y dy plus, because it's an or, the integral from 9 to 10 of the second branch, which is 2/5 minus 1/25y dy. And so for this one, we'll be plugging in to y squared over 50. That's the antiderivative of that from 0 to 2. Plus, this one's antiderivative was 2/5 y minus y squared over 50 from 9 to 10. For this first one, we're going to get 4 out of 50 minus 0. It's a pretty direct plug-in. For the second one, we're going to get, that's going to be 4 minus 2 for plugging in 10 minus, let's see, that's going to be 18 over 5 minus 81 over 50. We could clean up a little bit. That's 2/25 plus a 2 minus 18 over 5 minus 81 over 50. You could type all that into your calculator if you don't want to work it out by hand or get the common denominators. But it ends up being 5/50 is what it will reduce down to, which is 0.10. Now, before I move on to the next problem, it was hard to find a really good one in WebAssign that showed you how to go. We had this in the discrete cases where we went from our probability function to the cumulative function. We went from, okay, here's how the function relates to probabilities. And then we said, okay, now this is the cumulative one, which helps us with calculations. So I want to show you how to turn this into the cumulative function so that you could evaluate quicker for that. So I'm actually going to, oops, I'm going to have to pause and go get my battery real quick, but I'm going to pull up a Word document or another page of this so that I can show you the calculations for that. Okay, so this is the piece of how do I take, and this is from that number 2, how do I take my probability density function and turn it into that cumulative density function. So I'm just recopying it down, so we'll have it right here in front of us. And then it was 0 anywhere else. Okay, so the first step is you have to think about that graph again. And we had that we went from 0, 5 was in the middle. I'm just doing a rough sketch, and we had 10. And then we went up to all the way up to 0.2 for the height. And then that went back down. So rough sketch again. There are 2 separate areas that we need to be talking about because of the 2 rows. We have our A and our B. And when you're doing a CDF, it's a cumulative one. So when you talk about region B, you're also talking about all the area that came before it. So the first step is to get the area of A, which is just going to be integrating from 0 to Y, because Y is our variable. And then we're going to be kind of calling this generically. I'm going to use W. You could use any other variable you want, but we're integrating this, and then we're going to evaluate it at the start of our domain up to some unknown Y within that 0 to 5. It gives us a formula for the area for that part, that accumulating area. So that's going to be W squared over 50 from 0 to Y. So nothing new here. This is Y squared over 50. So for my CDF, which we always call capital F of the Y, that first line up there is going to be Y, 0 first, because we do want to start with 0, because before you even start our function, we had no area. Remember, it went less than 0 up and then greater than 10. Those were zeros. But that just means that at that point, but anywhere below that, we have not accumulated any area or any probability. So for Y less than 0, that's our first line. The second line is going to be, okay, if we are moving between 0 and 5, our accumulating probability there is going to be found by Y squared over 50. So that's from 0 included up to 5, but not included. Okay, so for this next part, you're going to be looking at B, which is going to be a combination of, if we're talking about the CDF, whatever happened in A up to a certain point here. We're letting it be Y because we're saying, okay, at some point here, we don't know where we're going to stop. We've accumulated up to a certain point of area, which included all of A and a portion of B. So my integral is going to look like similar setup. It's going to be 0 to, not 0, 5 to Y. Because this one starts at 5 for its first domain part. And we can say up to any point between 5 and 10. So the Y standing for that any value there. And this one's the 2/5 minus the 1/25 W dW plus our area of A evaluated from that 0 to 5. Okay. So we are going to need that area. Now, if you plug that into what we just got, we can get that accumulated area and know what the full area is for that region, which we just did when we were doing the previous problem. We know that that's 25 over 50 minus 0 and ends up being a half. So we're going to be adding a half because we were saying at that point, anything that's accumulated into this B region had 50% of the area of the entire graph was already covered. plus whatever additional we have. So then let's work this part out. This is going to be and go ahead and integrate that. So that's going to be 2/5 y, or excuse me, w. We are going to plug in y in just a second. Minus w squared over 25 or 50. I can't talk and think tonight. Sorry about that. And that's going to go from 5 to y plus this 1/2 at the end. Okay, that's the important part to getting your CDF correct, is not only integrating this piece, but adding all previous probabilities. If we had a third row, you'd integrate that region and add A and B's correct areas for their entire region to that at the end. So this is going to be 2/5 y minus y squared over 50. That's the first part. Minus 2. And then that's going to be minus a half, 25. Yeah, 25 over 50, which is a half. Then plus a half. This is -2 plus a half plus a half. That's going to be 2/5. I'm going to write it up here because I'm running out of room. So for part B, it's going to be 2/5 y minus y squared over 50, and that ends up being a -1. Okay, so you could leave it like that and plug it in and let it be a quadratic kind of in there, and maybe reorder it as y squared and y and then the -1. Or sometimes they'll clean some stuff up by like pulling out, for instance, I could pull out a 1 over 50 if I want to here, and think about this having a common denominator of 20 over 50 and a y, and I would only pull it out of the first two terms, and that would leave me with a 20 minus a y. So that's another way you could write it, is 1/50 y, parentheses 20 minus y, close parentheses -1. It's up to you. It really doesn't matter either way, because these are used to evaluate those cumulative probabilities. So if you want to leave it in its quadratic form, that's just fine. And that would be from 5 to 10, including both. And then we would need one more line that says after that point, we've reached the entire area. We've done the whole PDF essentially. So we've accumulated to 1. So if we get bigger than 10, we would have already had a cumulative probability area of 1. Everything had already come before that. So that's how you get the CDF from a probability density function. You have to integrate if it's this continuous random variable, and then you need to build each of those pieces on top of each other. So your individual distinct regions are always, yes, you're integrating this for some value in between there, but you have to add all complete previous areas from the previous regions. Okay, let's go up then, because I had one more example for this video, and that's this one. It says, let X denote the amount of time a book on a 2-hour reserve is actually checked out, and suppose the CDF is the following. It's very important to note what they've given you. This is a CDF. It also has a capital F, so that's telling you this is the accumulating function. So if we have anything where we're doing probabilities less than 0, we're going to get 0 because there is no area underneath that part. If we're between 0 and 4, we're going to use x squared over 16 to figure that out. And if we are greater than or equal to 4, we've already accumulated all of our areas. So that's a 1. So we're going to use the CDF to obtain the following. So this is the nice thing. When you are the CDF, you've already got the part to plug into. It's already been integrated for you, essentially. So for P of x less than or equal to 3, since that is less than, which is how these accumulate, you would just plug in f of 3. So that's going to be 9 over 16, which reduces down to decimal of 0.5625. If I want the probability of 2.5 less than or equal to x less than or equal to 3. Again, this is going to be kind of like evaluating your closed interval on your integration. So that's going to be f of 3 minus f of 2.5. That's 9/16 minus 2.5 squared. I didn't even work that out. 2.5 squared over 16. I just typed this into my calculator and got 0.1719 for the final answer there. Because you will want to use your calculator. I show all my work in the videos just to kind of help you guide along, but you can use calculators on certain portions, just at least write out what you typed into your calculator. For this one, it's probability greater than. So that's different than what we were doing. When we're accumulating the CDF, you're going, everything shades to the left. So we need to do a complement here and do 1 minus the probability that x is less than or equal to 3.5, which is 1 minus 3.5 squared over 16, or 1 minus 0.7656, which equals 0.2344. What is the median checkout duration? So mu tilde essentially. And this means you're solving for what value do we actually hit a probability accumulated of 0.5. So we set 0.5 equal to our mu tilde essentially, which is going to be mu tilde squared over 16, because that's our value for how we evaluate between 0 to 4, which is where all of our area is. We'll multiply both sides by 16, and that's going to come out to 8 equals mu tilde squared. Take a square root of that to get mu tilde. So mu tilde is going to be, which is our median, 2.8284. Okay, obtain the density function. So this is going the opposite direction. If you have the function for the probability density function, you have to integrate to get your cumulative one. Well, if you are going the opposite direction, if you have the cumulative and you want to know what your density function was, your PDF, you're going to be taking the derivative. So the only part we actually have to work on this one was that one piece. This was f of x when we're between 0 and 4. We take the derivative of that, that's going to equal our probability density function. So that's going to be 2x over 16, or just x over 8. So you can write that as 1/8 x or x over 8. Either one's okay. Okay, so let's talk about how do we calculate expected value when we're dealing with these continuous random variables, and our PDF is what you use to find this. So you do expected value is the integral from your whole domain. So we always just start off with negative infinity to infinity of all x values times your probability density function dx. And since ours is only defined in one row, essentially, because it's 0 everywhere else, that's going to go down to being 0 to 4 of x times the probability density function was x squared over 16 there, or not, sorry, x over 8. Talking and writing. That was our cumulative one. So we want to use our probability density function. So x over 8 dx. That's going to be 0 to 4 of x squared over 8 dx. That is x to the third, and we're going to multiply that 8 in the bottom by 3. So it's going to be over 24. And we're going to be going from 0 to 4. So that's going to be 64 over 24 minus 0 over 24. So 64 divided by 24 is 2.666 repeating. So if we round that to, I think it's 4 decimal places for all of these, it'll be 2.6667. So there's my expected value. Now, the next piece asks us to calculate the variance and the standard deviation. So variance, you can use the shortcut formula as long as you know your other piece. Now, we don't know the other piece yet. The shortcut formula for variance is variance of x is equal e of x squared minus e of x squared. So the expected value of x squared minus the expected value of x squared. We have the expected value of x. We don't have expected value of x squared yet, but that's really simple to find. You again integrate. And I'm going to go ahead and write from 0 to 4, but this time you do x squared times your PDF. So that's going to be 0 to 4 of x cubed over 8 dx. Use our power rule there. That's going to be x to the 4th on top over 3 times 8 would be 24 still in the bottom. Wait, no, we're multiplying by 4, 32. Yeah, you'd have to add 1 and then multiply the bottom by that new power. So that's going to be 32 from 0 to 4. And when I work that out, we'll see what we get. 4 to the 4th is 64. No. What is 4 to the 4th? It's not 64 because that's 4 to the 3rd. 4 to the 4th is 256. Okay. Divided by 32 and then minus 0. This is going to equal 8. It actually ends up coming out to a nice number. So our formula says, if we take that value, expected value of x squared minus the expected value of x and square that, that's going to give us our variance. So 0.8889. Now I will say if you use this version, you probably want to take it out a few more decimal places. We rounded it for this answer, but I think if you go out if you only go out this much, you actually don't get this rounding up to the 9. I think you're like at 8 or 7 here, so it messes up your rounding a little bit. If you'd left this as a reduced fraction, and let's see, what is that, 8/3, that gives you a way more accurate answer there. So, and then our standard deviation is the square root of the variance. So this is 0.9428. And then the last question, if the borrower is charged an amount of, this is our now kind of function of our random variable. So h of x equals x squared when checkout duration is x, compute the expected charge of E. Well, we already did this. We did it to do our variance part. So this is the same thing as E of x squared. So they should be expected to be charged 8. And I'm guessing we would normally write dollars in, but they don't usually like that on WebAssign. All right, so that is the end of this video.